Now that we've looked and understand a lot about the nature of the nucleus in an atom, in our next part we're going to take a look at the nature of electrons. Now in our model, we have a lot of choices for how we can include the electrons in our model, and specifically in how do these electrons move. Now one possible option is that the electrons are buzzing around in the electron cloud and that they're moving in just a random motion all over the place, such as you can see in this picture here. Now, one thing you need to understand about electrons is that their energy, the energy that that electron has, depends on its distance from the nucleus. So when your electron is close to the nucleus, it has a lower energy, and as the electron gets farther and farther away, the energy gets higher and higher. Now, a model that has a random motion of electrons would seem to indicate, well, at any given point in time, the electron could possess any possible amount of energy, depending on how far it is from the nucleus. So that's one option for how we could model our electrons. Now for some clues, for some evidence for what our model of the atom actually might have, we actually want to take a look at neon lights. We're all familiar with these lights. We have a gas inside of this tube. We hook it to a high voltage power supply, and when we do, the gas glows. And we actually get different colors of light that show up depending on what type of gas is present in that. The neon actually is the one that gives us kind of that orangey red color. Now, what does this have to do with electrons? Well, when they were looking at these neon lights, they were trying to make some predictions here. And according to our model, if you've got a model where your electrons are just randomly moving, then that means, again, at any given point in time, there would be some electrons in there that would have any possible energy. Because remember, in your tube of gas, you've got billions and billions and billions of atoms, and so there would be some electrons that would have any amount of energy. So what we would predict then is that our tube of gas would just be able to give off a huge variety, pretty much all different possible amounts of energy would be able to be given off. Now, of course, we would see it all mixed together with our eyes, and so some of that energy might be visible light, and so since it's all mixed together, we might see it as white light. Of course, we know that white light is actually a combination of all the different colors, and if we were to take that white light, such as light from the sun, and run it through a spectroscope, which is essentially just a fancy prism, we would see that the white light gets separated and we would get the full rainbow. And so, again, if this were the case, this type of random motion model predicts that when we look at the spectra of these guys, we would get what's called a continuous spectra. So down here, notice we have the full rainbow. That means that every possible amount of energy is given off. You need to understand that every color of light travels in waves, and every color of light has its own specific wavelength and its own specific frequency. So if my wavelength is about 500 nanometers, it's always going to be this blue-green color. When we get down to about 400 nanometers, we're talking about a violet type of a light. So if every possible energy was represented, my electrons are just randomly moving, we should see a whole variety. We should see the continuous spectrum. But what we actually find is if we were to put, say, some hydrogen gas in a tube, now when we look at it with just our eyes, we see everything mixed together. It's kind of a cool pinkish lavender color. But when we look at it through the spectroscope, instead of seeing a full rainbow, we see what's called a line spectra. There's only specific wavelengths of energy that are given off by the hydrogen. So this kind of sounds like that random model's not really what's going on, okay, because the electrons in hydrogen seem to only possess just few specific amounts of energy, we see represented by the lines here, and not just any random amount of energy. So using these observations, they started to build a model of the electron to include these observations. A model of the atom. And the famous model here is called the Bohr Model of the atom by Niels Bohr. And in his model, notice our electrons aren't just randomly moving around. His model is often called the solar system model for kind of obvious reasons. This looks like the sun in the center here, and it looks like we have our planets orbiting around the sun. Well, basically, his model says is that your electrons are present in certain fixed energy levels, very similarly to the way the planets have a fixed orbit that they are in around the sun. And so there's no random motion here. The electrons have just certain specific set amounts of energy, and so they're either on one of these energy levels, and notice we number them starting from the nucleus going out. So this would be energy level number 1, or maybe an electron is on the second energy level or on the third, and as we work our way out, 4, 5, and 6, and so forth. So the idea is that we don't have a random motion, we have just certain set energy levels that these electrons are in, and that would explain why they're only capable of giving off certain set amounts of energy, which is why we just get the line spectra as opposed to the continuous spectrum. So they're only going to exist on those energy levels. Now that does not mean that the electron is stuck on that particular energy level. It's possible that the electron could jump up an energy level. If that electron were to absorb some energy, so here comes some energy in, if that electron absorbs it, it might kick it up. Now my electron is higher in energy, so it's going to be on a higher energy level now. But the idea is that there's no in between. The electron is either on this energy level or it's on the second energy level. That's what we mean by quantized energy levels. Now, it's actually not as stable for this electron to be on a higher energy level. They like to be lower in energy. They like to be closer to the nucleus, typically. And so when it absorbed the energy and kicked it up to this higher level, the atom is said to be in the excited state. Excited state just means that your electrons are in a higher energy level than possible. They are not in the most stable configuration. And so they're in the excited state now. Well, since it's not as stable, it's not going to want to stay in this configuration. So what happens is the electron is going to want to jump back down, and it's going to go down to the more stable, what's called the ground state. And when it does this, we'll see it jump back down here. You can think about what's going to happen with energy here. Well, notice it gave off energy in this case. So if it absorbs the energy, it'll get kicked up to a higher level. Maybe it absorbed, let's just say, 10 joules of energy that kicked it up to the higher level. Well, when it jumps back down, it's going to give off the 10 joules of energy. So it's the same amount of energy, it's just given off as opposed to absorbing. And so now that it's in the most stable configuration again, the atom is said to be in the ground state. Now just a quick note about the ground state. Ground state does not mean that all of the electrons are always in the first energy level. It just means they are in the lowest possible energy level. Now, if I only have one electron, the lowest possible energy level is the first energy level. As you may remember from previous science classes, we can fit up to 2 electrons in the first energy level. So if I had 2 electrons, ground state means they'd both be in the first energy level. But if I had an atom that had 3 electrons, I could put 2 of them in the first, and then my third electron would be in the second energy level. And that would be the ground state for that particular one. So it doesn't mean they're all in the first, it just means that they're in the lowest possible configuration. Now, the electrons can jump up and down. So when we have a gas, like maybe we have lithium gas that's in here, and when the electrons absorb energy, they get kicked up to a higher energy level, but then they jump back down, and when they jump back down, they give off energy. And some of that energy that they give off, it's going to be electromagnetic radiation. So it might be infrared radiation, maybe some ultraviolet, but some of that is going to be in the visible light range. Because visible light is electromagnetic radiation. It travels in waves. And so we'll be able to see some of this. And when we separate it with the spectroscope, we can see that each line in our line spectra represents a specific jump that an electron is making. And whenever it makes that specific jump, it always gives off that specific amount of energy with that specific color. And so that explains this model. Now, every element is a little bit different because every element has its energy levels spaced out differently. So we look here, we see sodium. sodium is only capable of giving off one type of visible light, and that's this yellow light that we see here, whereas mercury can give off several types of yellow. So the energy levels are spaced differently, so that means when they jump, they give off different amounts of energy. And so these line spectra that we see for the different elements are very identifying. In fact, here's just a summary of all the different elements, and you can see everyone's got a slightly different line spectra. In fact, these line spectra are often called the fingerprints of an element. Because they're unique, we can use them actually to identify what elements we have. That's how we know what gases are present in stars. So in your packets on page 51, you have a chart that looks like this, and this chart represents every possible jump that an electron can make. And this is specific for a hydrogen atom. The lines that you see here represents the energy levels, so n equals 2, n equals 1 means energy level number 1, energy level number 2, and the arrows represent a specific jump that we have going on. Now remember, each jump is capable of giving off a specific amount of energy. And so for example here, we have when an electron jumps from level 4 to level 2, such as in this example, it always gives off energy, and if we follow the line, it happens to give off visible light, to give off this blue-green color. So every time it makes that jump, it gives off blue-green color, which has a wavelength of 486.1 nanometers. So we see the correlation here between the jump and the energy that it gives off. Now you can use your charts to answer certain questions. So, if we pick one of these arrows, that's n equals 3, again represents energy level number 3. If we wanted to find an electron that was jumping from level 3 to 2, we would see, well, here's the arrow representing that. And the arrow has a letter. This is letter A. And there's several different letter A's, but they're in a specific series. So this one's A in the Balmer series, whenever it jumps from 3 to 2. Now to figure out what the wavelength of the energy that is given off when it makes that jump, you go to the top side of that page. And on the top side of that page, you will see a line spectra where you'll see these letters. And so you'll want to find the Balmer series. You've got several different series on that page. So find the section labeled the Balmer series. You'll see a line. You want to find the line that's labeled A. And you can see that the wavelength, now on this chart here, that wavelength is about 650 nanometers. So every time an electron jumps from level 3 to level 2, it gives off energy. The energy always has a wavelength of 650 nanometers, which is going to be red light. So hydrogen is capable of giving off this red color. It's also capable of giving off a different jump, would give off this blue-green, and these blues and these violets. So you can use your chart to answer questions like this. So I'd like you to pause the video now and look at your page 51 and write down what is the wavelength of the energy given off when an electron jumps from level 6 down to level 3. And you can start the video once you have your answer written down. So write it down now. Okay, if you've used your charts correctly, you'll see that the arrow jumping from 6 to 3 is letter C in the Passion series. And if you go up to the top of the page, find the Passion series, see the lines, and find the line that's labeled C, and you'll see that it has a wavelength of about 11,100 angstroms. Just another example here. We can, again, this is just good for hydrogen, but we can figure out, well, what jump is going to make that particular blue, that kind of darker blue line? Well, we can see this blue line here has a wavelength of about 420 nanometers, and it's labeled C. And again, the visible light is actually just Balmer series. I'm zoomed in here on just the Balmer series. So we go to the arrows jumping, we find the Balmer series, and we find the arrow going from C, and we can see, we can see that C in the Balmer series is a jump from level 5 to level 2. So we've answered that question. When it jumps from 5 to 2, it always makes a blue light. And again, this is only good for hydrogen. So what we want to do now is we want to use the information that's on page 51. We've got those charts there. We can now go ahead and answer all the questions that are on page 52. Make sure you have those done. We will go over the answers in class tomorrow.